Okay, so we're starting in chapter 2 now, which is on sound waves. So sound waves are disturbance that travel through a medium as what we call longitudinal waves. So longitudinal waves, if you remember from the last chapter, travel like accordions, so in, out, in, out. So they're made by vibrations causing particles to compress and rarefy. So compression means they're coming together, rarefy means they're spreading out. So they carry the energy through anything, basically. So sound can travel through solids, liquids, and gases, and they don't carry the particles in the medium with it. They just basically transfer that energy from particle to particle to particle as they move through it. So we know that sounds move through solids. If you've ever knocked on a door and gotten into like someone's heard you on the other side, that means you're sending your sound waves through the door. So they're compressing and rarefying the particles of the door until they get through. And it should make sense, which we wouldn't know this because we don't live encased in solids, but actually sound waves travel a little bit faster in solids than they do in liquids or gases because the particles are closer together and stay closer together, so it's easier for those particles to move in and out as they move the sound waves through. But because we don't hear via a solid, we could never test this. We always hear through air. That's how we get sound waves into our bodies. Is through the air as they travel through our ears. So we don't have a solid in there to help us recognize this, but they actually do move faster in solids than they do in liquids and gases. Okay, so interactions of sound waves. So this would make sense that we're going to have sound waves interact with each other because there's lots of stuff going on all of the time. So an echo is a reflected sound wave. I'm sure you've heard an echo before, whether you've been in a gym or something, been in an empty gym, or you hear your voice kind of echo back to each other. Maybe you've been in a cave before and you recognize this, or anywhere where you're kind of in a silent area where there's no one else around to absorb those sound waves, and it's usually got to be a hard area because they're going to reflect a lot more off of something that's hard than like off of something that's soft, like in an area where you have couches or chairs or a bedroom or something like that. You're not going to hear as much reflected sound waves. You're not going to hear a lot of echoes in your house, but you might in a classroom or you might in a hallway there at school. But again, those reflected sound waves basically bounce off and come back to you, and so you hear that same sound that you just made. So hard surfaces are going to reflect more waves than soft surfaces. So soft surfaces will absorb waves. In fact, if you've ever been to like a movie theater or a concert hall of some sort, you'll notice that a lot of stuff around you is going to be soft, because they don't want a lot of reflection going on in those places. You want you to hear a good sound. And if you have a lot of reflection going on, it's hard for you to hear what you need to hear. So that's why gym's not a big deal. Everyone's yelling in the gym. Who cares if you don't hear everything perfectly? Bigger deal when you're watching a movie or a concert. Okay, so diffraction is another type of interaction. So this would be something going on out in the hallway, and it bends and goes into the classroom. Basically, it bends and it spreads out again. So if it gets to something it can't go through, but there's a small opening, it will just bend through that opening. So instead of reflecting, there'll be an opening there that causes those to bend together and then spread out again. Interference obviously be another way. They interact with each other in some way, so they can be destructive interference or constructive interference. It can make it get louder or it can make it get softer depending on how those two waves meet. So a couple different ways that you can interact. So reflection, and then there's diffraction as well. So interference things as well. Okay, speed of sound at room temperature is 343 meters per second. There's several things that affect the speed of sound, which is, we'll talk about how do we break the speed of sound later on in this section. But a couple things that affect that. Elasticity would be one. So the more, elasticity ability of a material to bounce back after being disturbed. So the more elastic the medium, the faster the sound travels in it. So for instance, a solid is fairly elastic because it can bounce back very easily. So the particles in a solid do kind of move and can move around a little bit, but not very much. And so they bounce back to their original positions very easily, which makes solids a very easy material for sound waves to move through because those particles kind of jostle around a little bit, but they move that sound wave through very quickly. Or something that's a little bit less elastic, like a liquid or a gas even, it's not going to move as quickly. And so there's a, on this slide here, there is a little table that shows you the speed of sound. It's much faster in things like cast iron and aluminum and glass, which are going to be some of your like more dense materials. And again, we're going to talk about temperature as well. But depending on like how dense it is, it's going to move a lot faster. Gas, depending on if it's cold or warm, is going to affect that as well. It's a little bit slower in cold air than it is in warm air because the particles are moving a little bit less fast in cold air than warm air. And then the same thing with fresh and salt water. Fresh water doesn't have as much particles in it, as many particles as salt water does, so that means that the particles are going to be moving slightly faster, are going to be a little bit easier for things to move through when you have salt water, because there's more particles in it. Okay, so another thing that can affect the speed of sound is density. Things that are denser is going to have a little bit less, it's a little bit slower in denser materials than it would be in less dense materials. So brass is a little bit more dense than aluminum, which means it's going to be a little bit slower through brass than aluminum. So density is how much matter there is, or mass there is in a given volume. And so that's going to affect the speed of sound. So far it's elasticity and density that affects the speed of sound. Okay, so the last thing is going to be the speed of sound is going to be affected by temperature. So lower temperatures are going to be slower. The speed of sound is going to be slower than higher temperatures. So Chuck Yeager first broke the sound barrier on October 14th, 1947. He did it in a plane, and he did it very early in the morning when it was fairly cold. He went a little bit higher altitude, so he was able to do it, so it's a little bit slower up there, not as dense. So because of that, he was able to break the sound barrier. So he made his plane fly faster than the speed of sound, which creates a shock wave, and you can actually hear when something breaks the sound barrier. But pretty interesting. They've actually broken it on land too. I don't have the exact date of that in my mind, but again, it was a very cool morning in a very wide open area. They could get his vehicle moving very, very quickly. And so that can happen. Again, it has to be fairly cool because the speed of sound slows down when that happens. Okay, so this is the end of the first section in chapter 2. Again, this is part of the packet that got sent home, or you can get it on PowerSchool Learning, or you can do it on a separate sheet of paper, and anyway, you can hand it in to me via taking a picture or whatever, what you've gotten done. So, enjoy!